talk about Kepler and Kepler's laws. Um, so before before Newton's law of universal gravitation, Kepler's laws were known. So Kepler was a mathematician, lived in the late 1500s, I think like I'm going to say around the 1570s to say the 1630s, somewhere in that range. And he knew this guy. This is kind of an informal lesson, but called Tycho Brahe, who was a astronomer, and he was rich. He was an aristocrat, and he had all kinds of awesome astronomical equipment made. Um, Not like the kind of astronomical equipment you'd have today, like telescopes and so on. Telescopes were probably just being invented around Kepler's lifetime, so Tycho was like a generation before Kepler. Um, but he had things like, gigantic, I don't know what you call these things, but you always see them, like, I want to say sextant, but it's not really a sextant, but one of these things where you can point it at a star and figure out its angle and its altitude and so on. I don't know what you call these things. But anyway, yeah, they're circular. Anyway, you had all of these kinds of great old-fashioned astronomical equipment. Let me see if I can find a picture. Okay, so, this is the kind of thing we're talking about. Altimeters and so on, and angle measurers and so on. You had gigantic, massive, super expensive, well-constructed versions of these guys. And for 40 years, Tycho observed the locations of the planets, and so he had this massive amount of data. So we had this massive trove of data. And Kepler sought out Tycho and kind of became his, like, I'm going to say assistant. Somehow they were associated. And Kepler had a brilliant mathematical mind, whereas Tycho, I don't think did. Well, I'm not exactly sure. But anyway, they viewed the way that the planets moved in different ways. So Tycho, um, he was like a Platonic, if you want, or a Ptolemaic, I guess is a better word, which just means that they subscribed to the old Greek view that Earth was the center of the universe, right? And Kepler, although he probably never told Tycho this, was maybe not when he first met him a Copernican, but eventually a Copernican, okay? Which is sun centered, right? And so after some time, Tycho Brahe died, and Kepler somehow got a hold of his all of his data. Some people say he stole it because the family did not want to give it to him for some reason. Okay, um, so I'm not sure exactly how these two had a relationship, but anyway, somehow Kepler got away with these 40 years worth of observations, and then through just pure hard grunt work mathematics, he figured out three laws. The first is one, law of ellipses. In other words, planets move on elliptical orbits. Second is the law of equal areas. It's a little harder to explain. So first here, when we say elliptical orbits, people often think we mean like this, right? There are some things that go in an orbit like that if this is the sun, and those would be comets, but he wasn't looking at comets, he was looking at planets. Yeah, well, it's nearly perfectly circular. Like it's very close to being a perfect circle, but it is just slightly egg-shaped. Okay, and it's always drawn in an exaggerated way so that you can figure out some other stuff. Okay, so that's the first law, that you have elliptical kind of orbits. The second is the law of equal areas. What that means is, if this is area A and this is area B, right, these areas shaded, that an object orbiting around sweeps out an equal area in an equal amount of time. In other words, time from 1 to 2 on B takes the same amount of time as 1 to 2 on A if we're going this way. So what that must mean then is the planet moves faster when it's closer to the sun. Okay, so we figured that out mathematically. Law of equal areas. So this area A is equal to area B. And that is swept out in equal time. Okay, so what that implies then is that the planet must be moving faster when it's over here. Okay, so planets do not have constant speed, is what we're getting at there. And the last one is, I don't know what the name of this is, but the universal constant, if you want. And basically, it's this: that for a single orbital system, like the sun and the planets going around it, if you take the cube of the average orbital radius over the square of the period for the rotation, you get a constant. So what that means in practice is, if I take r cubed for t squared of any planet going around the sun, say Mars, that will be equal to the r cubed over t squared of any other planet in the solar system, Jupiter, or any other planet, right? It does not work for the moon because the moon is orbiting Earth, but it would work for the moon and satellites going around the Earth. Okay, so this was figured out before Newton, right? So some stuff was known, like basically this is proved mathematically by Kepler, the law of ellipses, and Newton was trying to say, well, what kind of relationship causes elliptical orbits? Kepler never really tried to explain the why. He just mathematically crunched out the numbers until he got these relationships. It just means that if I took any planet going around the sun and I took the cube of its radius, orbital radius, divided by the square of its time period to go around, I get the same number. Whether I do that for Earth, Mars, Jupiter, Neptune, anything going around the sun, you'll get the same value if you do this. The question is that backed up by what Newton said? All right, so Kepler's laws are interesting. They're useful. You can still use them if you want, even as a shortcut. If you know an orbital radius in a period, you can figure out, and you know the orbital radius of another planet, you can quickly figure out the relationship here. But you can also do the same thing with Newton's laws. So let's do a quick example of that and see how we can get this pulled out of Newton's laws. Okay, so for a planet going around the sun, Fc is provided by Fg, right? So Fc is mv squared over r, which is equal to g big M little m all over r squared. So here are the two masses. So the first thing we notice, if we're talking about planets going around the sun, here's the planet, here's the sun. All of a sudden the planet becomes irrelevant. In other words, it cancels out. We can divide m off each side. We can also get rid of one of the radii here, like that. Okay. So you get this. Velocity squared is equal to g m over r. Okay, which I think we maybe have already found. Okay, I mean, you can derive this if you ever need it. This still doesn't lead us back to this idea. Okay, so remember that the velocity of a planet actually is distance over time for its circumference, right? So if this is r, the circumference around is 2 pi r. And if you want velocity, you have to divide that by t. So the velocity of the planet should be 2 pi r over t. So then we're going to do a little substitution here, and we're going to say 2 pi r over t squared equals g m over r. And I'll square everything inside of here. So we'll get 4 pi squared r squared over t squared equals g m over r. And then we'll do some rearranging. We'll multiply both sides by r. And we'll get that r cubed over t squared So I have 4 pi squared here, but we're going to get rid of it in a second, equals gm. Divide 4 pi squared off each side, and you get this. So this is actually equivalent to Kepler's constant. I mean, it's going to be different for any orbital system, but if you're talking about the sun and the planets, right, this number will be true no matter which planet you look at. It has to be, right? Look at the way the math works out. So Kepler figured this out. Newton didn't refigure it out, but he put a different spin on it, and it all jives together, right? So, Newton had a famous saying. He said, "If I've seen further, it's because I have stood on the shoulders of giants," which is kind of a good little metaphor for the way that science works, and knowledge works, and knowledge gets passed on, right? People before you got you so far, you don't have to redo what they did from scratch. You get a little bit, you see a little bit further, and then you pass that on to the next guy, right? So Kepler and Galileo passed on to Newton. Newton passed on to guys that came after, and eventually you end up at Einstein, and you end up beyond Einstein. So that's kind of the way it goes. And that is our lesson.